to algebraic effects and handlers. So just to very quickly recap from what we taught last lecture, we talked about what is an algebraic effect. So an algebraic effect is given by the set of operations with signatures and a set of axioms that we usually expect them to respect, but sometimes they don't. And we talked very briefly about what algebraicity is and how computational programs can be considered computational programs can be considered as computational trees and how they relate to free monads. So what comes after is we are going to very quickly talk about generic effects, and this is the form of effects that people usually implement in their languages because it's easier to program this. And afterwards, we will be talking about effect handlers and how you can actually do something to those effects based on user customized behaviors. So let's start with generic effects. So from last lecture, we talked about this one Boolean location, right? We said, okay, there are three operations with signatures where put T, put F have signature 1. The connection somehow is not very stable. Okay. And get is an operation with signature 2. And we talked about some example programs you can write with this set of operations with variables. Like if you can do put T and then do whatever M says it will be doing. You can do get that will take 2 computations, and depending on the value, it will do something different. But now here is one question, right? We talked about one Boolean location. So we had 3 operations for this Boolean operation, like get T, get F, and put T, put F, and get. How can we generalize it to locations that can store natural numbers? How many operations would you need? Yes? Infinite many. Yes. But this is not how you would like to program with this set of infinite operations, right? This is going to be bad. And also, if you have a lot of locations with lots of natural numbers, then you would usually want to say, okay, which particular location would you like to get this number from? Because you may have different locations that store different numbers. So what we are going to do is we are going to generalize algebraic effect operations to what we call parameterized operations. So they are basically the set of the operations that can take parameters. So previously, they just have a signature that says how many, the arity, so how many computations it can take. And in this case, it also takes the parameters. Like in this case, we will say we have 2 operations that can use to access and update the content from the locations. And the operation update, it takes 2 arguments. First is the location you want to update the number to. And there is the natural number that you want to use to actually update that location. And then afterwards, the arity is still 1 because it still just takes 1 computation and then run whatever what that computation is. And now we have another operation called lookup that also takes a parameter location because you have to tell it in which location you want to get this number. And then it will take as many as natural number say that there are possible combinations, right? Because you have to enumerate all the possibilities. Just like in the case of get, we will have 2 computations. In the case of lookup, now you will have as many computations as natural numbers. And now what we can do is we can write this update. We can use this update operation, right? We can use this update. And you can compare how we write this operation from how we wrote the operation on the previous slide with get and put. Now this update takes 2 arguments you can consider this way. And the first argument is what this operation says it will actually take. And then the second is the original arity, which is 1. So in this case, it's just n. And then now we have an operation that says I'm going to update the location L with the number 42. And afterwards, I'm going to continue with this computation M. Yes?
Does this mean that when I use lookup, I have infinitely many configurations? Or
That's exactly my next question. Yes. So now we we can write this update update operation, but how can we write this lookup operation, right? I can give it a location that I want, but how many computations should I give it to? I will have to write an infinite term, because I have to say all the possibilities that should happen depending on what value is stored in that location. And of course, we will not be able to do that in a finite language. So instead, what we are going to do is we are going to generalize a little bit again, but this is just really an equivalent form in which you can write algebraic operations, which is called parameterized arguments. So in this case, this lookup, let's look at this lookup operation first. So in this case, it will only take one computation. And this computation now is a function. And the function says, if you get me back an x, which is the value that you store in that location, I'm going to do some m. And this m could depend on x, right? And now you only need to write a single computation for the also possibilities, because maybe you only care about whether the value stored there is 42 or not. And in all the other cases, you will behave exactly the same. And just for consistency, I also rewrite the program with update. Now I also make it a function, but in this case, because alt is wrong, so there are no information you can get from this argument, but you just give it an argument anyways, and in this case, it's just something like a unit. We have just basically updated the forms that you can write algebraic operations, and sometimes they come with convenience, right? But it's exactly like the same set of algebraic operations, that in the sense that there is still a set of signatures, and there is still a set of axioms that you would expect them to respect. Here, I didn't include all the axioms, but as what you can imagine, for example, if you look up a condition twice without changing in the middle, then it should be equivalent to just one lookup. And if you update it twice to the same location with different values, then the second update should overwrite the first update. But I didn't include all those axioms. But as you can see, we can still write axioms in this form, right? It's really a different form to write those operations. And now you might wonder, well, we have changed the form of operations. Should we change the definition of algebraicity? And if you still remember, previously we have defined algebraicity in the sense that the operations will commute with the evaluation context. So we can always push the evaluation context into those computation arguments. And it's the same case here. It's just that it's written differently. So in the case of the operation, well, you first have this parameter, because now we are in the parameterized operations. And then you have this computation that is a function. And you will push this evaluation context inside this function. But this evaluation context should change the parameter, because the parameter is always the parameter to the argument. But what happens afterwards would be commuting with the surrounding evaluation context. Yes?
So the first parameter to the operation is special because it's always going to be like the location.
Exactly. Like the argument you want to use to provide to the operation. But you could also imagine you can write an infinite number of operations that says put 1, put 2, put 3, put 4. This is just a way to sort of distinguish between different operations. Some examples with this lookup. For example, if you try to look up something from the location L, and afterwards you are going to do the computation M, and then it would be the equivalent, and then this whole thing is applied to this M. Then you can just push this M in as an argument to this M, because whatever function you got from this location in the M is going to be applied to M. So you could have just pushed it in. And similarly, if this lookup is used in argument position, then you can also push this whole function to the inside, because whatever you get from this location, you are going to provide it as an argument to this function. So this is just an example of algebraicities written in different ways for this form of algebraic operations. Okay, so, but we are not done yet. So there is also a concept called generic effects that people have actually proven to be equivalent to algebraic operations. And it turns out it's much easier to program with generic effects. So all the languages that we have seen that have implemented algebraic effects, they implement generic effects. So what are generic effects? Well, this is what we have reached to so far, right? This is now how we write programs with operations. We provided the argument, and then we provide the, you can consider it as continuations, but a concept that we will make clear later, that the computation will depend on the result you get from the location. But always writing this computation is annoying, right? Like now you have to write the arguments and you have to tell it exactly what's going to happen afterwards. But why can't I just consider a set of operations with this kind of type signatures? So I will just say, no, I write two operations corresponding to the generic effect version of the operations above. I will just say gen update generic effect. Gen update M is the program where if M has this type, which has both the location and the natural number, then gen update M will just give you back a unit. And you can do whatever you want with the unit. But I don't care. All I know is I will give you back a unit. And similarly, for the lookup, if you give me a location M, then I will give you back a natural number. And you can do whatever you want with this natural number. And now you can compare what we write below with what we have above. So in this case, we will just say if you want to update the location L with 42, fine, update it, you will get back a unit. And you can do whatever you want with this unit afterwards, but you don't have to tell me exactly what happens. And similarly, this gen lookup, you can just give it a location and then you will get back a natural number. And you can do what you want with this natural number. I have already said a little bit about their equivalence, but one question that you could think about it for a bit is, are they equivalent? Like, is the form above actually equivalent to the form below in the sense that they can actually express each other? I see some nodding. Okay. Why do you think they are not equivalent?
It seems like in the top side we track really well like where we're going next. On the bottom, I can't tell if we are always going to go to the line below but I don't know. I'm not sure.
Yeah.
We're explicitly binding the alpha to the net in the first example. Sorry, we're explicitly binding the x in the first example, so I don't know what free variable in and it would be down to in the generic effect.
So you worry about the binding?
Yeah.
There was some hand in the back? Yeah. Oh, sorry. Yes.
I mean, it seems to me like these are the algebraic operations version is sort of just wrapping some like let bindings around the generic effects version. They seem very, very similar now.
Yeah, that's a very good point. So algebraic effects are basically let binding the result of this operation. And that's exactly the point that you can actually prove algebraic operations and the generic effects are equivalent. And this is how you can express one in the other. So if you have generic effects like gen update location L with 42, then you can express it exactly as the form in the, I think I should the order, it should be the other way around. So this one is the generic effect and this one is the algebraic operation. And you could just give the function that is the identity function. That you get back the value and just return it. And after you return it, you can do whatever with it in the rest of the program. And similarly, if you have an algebraic operation that says I'm going to do some n depending on this value of x, and then we can exactly just like finding this result you get from that location, and then continue with n. So you can see once we have light bounded, this x becomes available in n again, and you can do computations depending on the value of x. So this equivalence is not so obvious. This is why we may have different first answers to this question, and this is also why this question deserves the whole paper by itself. So there is this paper by Gordon Plotkin and John Power in 2003 where they proved that the algebraic operations and generic effects are actually equivalent. But we are not going to expand on that, but in case you're interested, you can look it up. Okay, so like I said, generic effects are actually what people implement in languages, because as you can see, it's much easier to program. Right? You just give it an argument and you get back the return result, and then you do whatever in the rest of the program. So that's a lot about algebraic operations and generic effects. So let's actually get into a lambda calculus that has algebraic effects. And we are going to use generic effects for the rest of the lecture because they are much easier to program. But we haven't reached the effect handlers. That's going to be immediately after this part. But let's see what language construct we have got so far. So let's consider that we are in lambda calculus. So I don't have types yet. It's the abstract lambda calculus, where you have some constant c, and you have variable x, you have a lambda, you have a function, and then you have if and else expressions. It's just because we will use them to write examples. And then we have a form of operation, so I have highlighted it, it's in blue. And whenever you call this operation, you have to provide an argument e. And we will only say that the constants and the lambdas, they are values. And all the others, they are not values. And we can define evaluation context. We don't use the definition of evaluation context yet, but we will have to use it when we have handlers, so you will see that soon. And in this case, evaluation context is either empty. So again, to remind you, evaluation context is basically an expression with a hole, and you can plug in an expression into that hole to make this a complete expression. But evaluation context basically tells you the evaluation order of things, and in this case, it's like you have to evaluate the functions first before you can evaluate its argument. So the evaluation context is either empty, or you try to evaluate the function. Or the function is already a value, you try to evaluate its argument, or you evaluate the bracket in the if and else expression, and you could also try to evaluate the argument of the operation if it's not a value yet. Yes?
Sorry, to make sure I understand, the reason we split into the E and the V is so that we ensure that if something is a function applied to an argument, that function is already evaluated as much as possible?
You have to evaluate that function first before you can evaluate the value.
And that's the reason for the E and V split?
Yeah.
Okay.
And I have here 3 reduction rules. The first one is the usual data reduction, where we reduce the lambda when it's applied to a value, and the second method they just reduce if there are else expressions. If it's true, evaluate E2. If it's false, evaluate E3. But I haven't told you like how to evaluate operations, right? If you have operations, then what happens? Well, even before we talk about that, right? Just with this simple program, simple calculus, you can already start writing programs. For example, here I gave an example with 2 effects, 2 operations with signatures. So I will say choose is operation that takes the unit and gets back the boolean. Well, we haven't talked about types yet, but hopefully this gives you some intuition about what's happening. And the fail is basically the exception operation that takes the unit and returns. It can return what like anything, right? Because you have fails. I just put a temp variable a there. And you can use this set of operations to write programs, right? If you want to toss a coin, for example, here is a program toss that takes a unit, and then it calls this operation choose. And operation returns you back a boolean, as we have seen in the generic effects definition. And if it's true, we are going to return heads. Otherwise, we are going to return tails. And you can also try to toss a coin when you're drunk. But that means tossing a coin could fail. So in this case, we are using two effects in a single program, right? We will first say, okay, we will call choose once, and only if it returns true, we are actually going to toss the coin. Otherwise, we will just call fail. And you can see that we started using multiple operations in a single program. But so far, I still haven't told you how should we destruct effect operations, right? Now, according to the operational semantics, the program will just get stuck whenever you see an operation. So that's exactly what effect handlers do. So what are effect handlers? You will hear maybe many people describe effect handlers in different ways. You will hear them saying that effect handlers are effect destructors if you consider algebraic operations as effect construct. And you could also hear people saying effect handlers are a modular interpretation of effect operations, or they are resumable exception handlers. So if you have an exception, then sometimes maybe you don't want to just fail, but you want to resume the original computation by some default value, for example. Or you can also consider it as a fault over the computational tree. Or if you have heard about the word delimited control operators, people consider effect handlers as structured delimited control operators. We'll get to the point about delimited continuation soon. And in the category sense, people also say effect handlers are a morphism between three algebras because they map one algebraic structure into another algebraic structure. So what exactly are effect handlers? Like, there are so many ways to describe them. And here I gave the syntax of effect handlers. So what is in this syntax? So we have four parts. First, we have the handle keyword. So I will just use the handle keyword to say that we are handling a computation using a handler. And then we have this handler definition within these curly brackets. And we have a computation comes afterwards, that is the computation you are trying to handle. And what we are trying to handle here, within this handler definition, we have two parts. We have this operation maps to something, which is a function. And then there is something called a return that maps to some other function. And in this op syntax, you can consider that this operation is saying, I'm going to handle the operation op if there is an op in the computation that I'm handling, which is E. And how am I going to handle it? I'm going to bind X to the argument you provide to the operation. And I'm going to bind K to the delimited continuation. We will revisit what is delimited continuation. And afterwards, I'm going to evaluate E1. So basically, if you ever perform the operation in your program and it is handled by some handler, you would switch the control of your program to that handler. And now a handler decides what to do afterwards. And the handler decides that by having access both the argument to provide the operation and the delimited continuation. And that does something with E1. And we have another clause within this handler definition that is called a return. And sometimes return is very convenient if the computation just returns a normal value. And this return clause only applies when the computation returns a value without performing an operation. And in that case, we are going to find the value of this computation to X, and then we are going to evaluate E2. So I said here that X binds the operation argument. This is what we all know because no operation takes an argument. And K binds a delimited continuation. So what is a delimited continuation? A delimited continuation is basically, of course, a continuation. So what is a continuation? A continuation, you can consider it as a function. It takes the value of your program and then continue with something. So this is why it's called continuation. And delimited continuation is continuation that does not capture the whole rest of the program, but is delimited at a certain point. So in the case of effect handlers, this delimited continuation will capture from where the operation is performed to where the handler is used to handle this operation. That where the handler is in the evaluation context for the handler used to handle this operation. So more precisely, if you perform an operation in your program, let's say your program currently looks like this. So you have a handler available in the evaluation context. So we will extend the definition of evaluation context with handlers. If you have a handler in the evaluation context, and now the thing you are currently evaluating is an operation. Like this operation needs to be handled now. It is the thing that you are evaluating. Then what I'm going to do, I'm going to find the innermost handler in the evaluation context. Because there might be multiple handlers for the same operation. But I'm always going to handle it using the innermost handler. So this is what this operation, this notion says. Basically, no other handler in the evaluation context E will handle this operation. And then I'm going to bind this whole the evaluation context between this operation until this handler as the delimited continuation. So in this case, if we think again about the definition of the handler in that operation takes the x and takes the k, right? And in this case, x will just bind this v because that's the argument of the operation. And so now the question is really, what would that k bind? And we say that this k binds the delimited continuation because we can consider this k as a function. And this function says, if you give me back the operation, the result of this operation, in this case, I represented x, I'm going to continue the original computation. So this is the function that says, I'm waiting for the result of this operation. And once I have it, I'm going to plug it back to the original evaluation context where this operation is performed. And in this case, we also reinstall this handler as part of the continuation because that would allow you to perform the same operation again. Got it? Okay.
So remind me that E is something with a hole in it, and the square brackets correspond to plugging the hole with what's in the brackets.
Exactly.
Okay.
So the capital E is an evaluation context that has a hole, that is basically expression with a hole, and this bracket notation is plug in whatever this expression is into that hole. And because evaluation context tells you what you should evaluate next, this expression is currently at the state that you are going to evaluate this operation. This operation is the thing that you are evaluating. And once you get the result of the operation, maybe you're binding somewhere, maybe you want to add 1 to it, add 2 to it. So that's the rest of what's happening in this evaluation context. And then this whole thing is wrapped inside this handler. All make sense? Okay, so let's see a few examples. Maybe it will start to make more sense. So consider that we are handling that exception operation, right? We have seen that fail operation. So this maybe fail on the left is a handler for that fail operation. And as we have seen, a handler has to define 2 clauses. The first is the operation, and the second is the return clause. And in this case, this handler for this fail operation says, if your program have ever code fail, then I don't care about the operation you pass to me, and I don't care about the continuation either. I will just turn the whole result of this handle expression to nothing. And otherwise, if your computation returns normally, then I know this x is bound about the value of the result of the computation, and I'm going to wrap this value within just. So I'm basically turning the type of the whole program into a maybe. So there are some examples on the right. So if we handle 42 with a maybe fail, then at that point, the computation being handled is already a value. So it's trying to return from the handler. It's already a value. And in that case, we apply this return clause and wrap 42 within just, and we get just a 42. Otherwise, if the program you are handling is actually currently performing an operation, like in this case fail with argument unit, now this handler will say, I don't care about the rest of the computation. Now the whole thing is just a nothing. So the handler has successfully turned the type of this program into a maybe type. And because you have this continuation available, right? In the case of exception, maybe you say that we don't care about the continuation because we will just abort the computation altogether. But because you have this continuation available, you can actually resume from the original computation. So this true choice is a handler that handles the choose operation. We have seen that we use to toss a coin. And in this case, this handler says, well, if we ever perform choose, I'm going to resume the original handler by giving back 2. Or otherwise, if your computation just returns normally, then nothing is going to happen. I will just apply this identity function. Yes?
So this true choice makes choose no longer non-deterministic. It makes choose now give you true every time?
Yes. Yes, exactly. So every time you call choose now, you will get back a true. Basically, this is what this handler is saying. So again, if you handle 42 with true choice, nothing is going to happen because the identity function applies, you get back 42. And if you handle the program to toss a coin that we have seen on the previous slide, then because you always get back 2, in this case, you will just get pass back. And because, again, we have this continuation available, right? I mean, you can do whatever you want with this continuation. For example, you can actually resume the original computation twice and turn the type of the program into a list. So in this case, all choices is again a handler for the choose operation, but it does something different because now you can do what you want to do in the effect handler in different ways because they are useful under different contexts. So what is happening here? This is saying, well, maybe let's look at the return clause first. If your computation returns normally, then I'm going to wrap the computation value inside a list. And now you get back a singleton list. But if you have performed the choose, then I'm going to first resume with